All right, so you can do a lot of calculus on your calculator, right? You can do that. A lot of calculus on your calculator. You know how to do derivatives, right? Or how to find the values of derivatives? Okay, let me show you something. All right, so I'm going to show you the graphical method of doing this first, and then I'm going to show you a different method. But if we want to, let's graph the function on this interval. So we get, okay, so we get x minus x squared divided by 2 times the cube root. So we can actually do a cube root on here, but it's a lot easier just to do a what power?
X to the 1/3.
1/3.
Oh, I just did the math.
It was pretty easy on mine.
You just go math and then
Like 4 or whatever.
Okay, we good? Hunter, are we good?
Yeah.
Okay. Let's put that away, please.
He's
Oh, it's
calculating.
calculator. Okay. All right. So let's graph this. Let's go. So what would probably be a good interval for me to do this on? Okay, I could go -8 to -1. That would be fine. If I want to give myself just a little bit of extra so I can kind of see the edges, how about that? Okay, so when I set the x values, remember there's a good trick. You can let the calculator fit the y values to the function. So you just go zoom 0, which on the menu is called zoom fit. And it does this. Okay, so it's graphing the function.
It's going. So it's quicker than one.
Say it again. Right, those are x values, right? So we're adding up the area under the curve. Hunter, are you done with it? Okay. All right, but I just keep talking. So we're going from -8 to -1, right? Those are the x values, right? We're trying to add up the area under the curve between x equals -8 and x equals -1, right? Okay, so here's the curve. We don't even know where the y-axis is, where the x-axis is. I mean, we could size the window so we could see it, but it's not important. It's fine. This is the function. You know what? Actually, I'm going to. Let me just go to the menu, or to the window, and the y's go from just over 0 to 25.5 something. So I'm going to, just so we can see the axis, I'm going to change this one right here to, like, y minimum to -1. And regraph it.
Wait, when did you put it in?
I just manually changed the bottom of the window to be -1. Y minimum to be -1, just so it's a little bit lower than it was before, so we can see the x-axis. Not critical to do
What did
that.
you put into the Y box? I'm still there.
In the y box, I just put that function.
How did you get the -1 to?
Oh, I didn't do that. I'm just doing the function, right? So all I graphed was this, right? That's f of x. That's the function under which we're going to add up the area, right? Because really all we're doing here is just a definite integral, which always looks like this. The integral of f of x dx from a to b. So f of x is this, a is -8, b is -1, and we're going to find the area under the curve, okay? So, so there it is. To find the area under the curve then, we're just going to go to the calculate menu inside the graph. So once we've got it graphed, we'll go second F4, which is calc. And which one do you think we want? Yeah, number 7. So if we choose number 7, then it just wants to know what's the lower limit. No,
-5.
-8, right? A is going to be the lower limit always, right? gonna be the one that's furthest to the left, so -8 is the lower limit. So when the calculator prompts you like that, you have to input something and hit enter, right? It wanted to know what the lower limit was, so I enter -8 and hit enter again. Now it wants the upper limit. Look what it did. It grabbed -8 as the left-hand edge. So when I enter -1 and hit enter, look what it does.
I'm so.
How did you do the negative y? How'd you do, yeah, negative y. How'd you do the second one? I got to negative
It just prompts me to do it.
x equals -8 and how'd you do it?
Okay, so we'll do it again. But part of the problem is people in the back are having a hard time hearing me because some people are just talking incessantly, rudely, while other people are unable to hear what I'm saying. So please stop. This is wasting our time. Let me do it again. So we go back up to, so all we do here is we're just entering the function, right? And we're going to add the area up under the curve. So we got to get the graph first. So everybody's, you won't have that part yet, right? Yours is just going to look like just a graph, right? So once you get the function graphed, then you go to the calculate menu. You go second, calculate, and then we're going to choose which one of these things do we want to do with the graph. Well, we want to do number 7, which is add up that looks like calculus, right? So we're adding up an area under the curve f of x. So we would just go 7, and then it's going to prompt us. See, it gives us a little message. It says lower limit question mark. That means it expects us to give it an answer. The calculator does. It wants to know what's the lower limit. Well, the lower limit is just right there, right? Because we're adding up the area under the curve from this x value up to that x value, right? And so we're just going to enter the value -8, enter. Now it's prompting us again. It wants an upper limit. So it knows that we're gonna this is our left boundary, right? It wants the right-hand edge of the area though. So we need to enter -1, enter. And then it thinks for a second and it gives me this answer. It hasn't given me the answer yet, but it will.
It's 7.11.
Right, and it's still thinking. There it is. So it's telling me then, and that look, it gives me all the information. It summarizes what I just did. The area under the function f of x dx from -8 to -1 is 57.1125. So numerically, the bad part about it is, what if it's a non-terminated decimal? It's an irrational answer. Then we're not getting an exact answer. We're just getting an approximate answer. That's pretty good, right? I mean, that tells us what the area under the curve is. That's it.
If we accidentally put the negative on the way to calculate, will it
Okay,
compare signs?
well, let's see what, no, I don't think so. Let's see what happens. What if we do that? So if we go back to second calc, does anybody want to make a prediction? What should it do? Should be negative. Right, so if I go 7, lower limit, if I do -1, and upper limit -8, it's thinking. And it gives me a negative area, which it should do, right? Because I added positive area up backwards, which makes it negative. Remember our sign convention? Lower limit. That looks good. Okay. Upper limit. So go to web. Oh, see your X max, you just don't, you have to go to the cursor. So you'd have to go from like, -3 is less than -1. So I have to do something like that. See what I'm saying? You have to have both the limits have to be.
I did that on a screen, but I went to window and did that. Okay.
Does that make sense?
Yeah.
Okay.
I haven't done familiar calculus.
So let me just head this one off your pass, because Alexis had this question. She got an error, but the error she got was because she didn't have on her screen, she wasn't showing the function over this interval, right? Like if I define the interval, like if I went from, let's say, -8 to -3 or something on the screen, and I asked the calculator for the area between -8 and -1, well, the part of the area is not on the screen, and the calculator won't calculate numerical values it's not represented on the screen. It is a little weird. Okay. Did it do it now?
Yeah, but it's not looking the same.
Well, okay, that's only because your scale's a little different. No big deal. Like if I stretch this one out a little bit, it would look different also. Okay, so there's another way to do this one though. You can do this graphically, which is fine. And the nice thing about doing it graphically is now I've got the function, and so if I wanted to go back, there's other things I can do also. Like I could, for example, what if I want to know the derivative of the function at x equals -5? Yeah, I can do that. I can go second, calculate. Which one do you think is going to tell me the slope? dy dx. So I'll just choose number 6, and it wants to know and then I can just enter an x value. So if I enter -5, enter, look what it does. It puts the cursor on that point, and it tells me the value of the derivative there. And the value of the function for that matter, which is kind of nice. Okay?
Wait, mine didn't give me the value.
Why were we not doing this?
They didn't want you to do it before.
I know.
Yeah.
Wait, honey,
This is
so
how math
value
always
of
works. You learn how to do it in the calculator in the very next chapter.
Yeah. So questions on this?
Mine didn't give me the.
What's the value of the derivative mean again?
The slope. Slope of the tangent line.
Sorry, how did
Okay.
you do that?
Okay, so one more time. Here's what you do. So once you've got it graphed, you go second, calc, 6, and then you just type in. You can use the cursor by just skipping along the function, but that's no good because it's not probably going to go to the exact place you want it to. So then you just enter an x value. Like I'll go -6 this time. So I enter x equals -6, enter, and it puts me right at x equals -6, and it gives me back the y value and the derivative.
I'm not getting the derivative.
It's not showing
I
up.
get it. I'm
You have to
defined.
do it again.
I don't.
If like we said.
No, I'm not getting it. I'm defined.
Okay, so
Looks like -2.
maybe you're. Did it work? Oh, yeah. What'd you do?
So you do dy/dx.
Yeah. Yeah, yours is different.
That's what I did the first time. It works like the same thing, but I mean, like after I do that, I just pick it off my comment.
Yeah.
Oh, shoot.
Mine just
Yeah,
gave
you
me-
do have to keep redoing it. Though.
Mine didn't give me x and y.
Why did it give me X?
It just gave you x.
It just gave me the
2.63, is that it?
Yeah, it doesn't give me the x
Sarah, why is
and
it?
y. Just gives me the dy/dx.
Okay, let's.
It's gotta be the silver edition.
Then you
I have
have
the
to-
silver edition. It's the plus C.
Let's try one other thing. So.
Aren't you gonna show us a better way to do this?
Well, not a better way, just a different way. So I don't see anything on here that has any impact on this.
But this is a different version.
You might. It's possible you need to update your operating system on your calculator if it doesn't do that. That could be it too. It's
Yeah.
easy to do.
I'm pretty sure that's it.
Yeah. Okay, so here's another way to do it. Let's look at the other non-graphical way of doing this problem. So we can also just go from the home screen. We can go directly to math, and we want to go to number 9. That means finite integral. Okay, so you just go number 9, and look what it does. It gives you back a template that looks just like a definite integral, right?
Wait, number 9.
And so I can just go from, just fill in the blanks, -8, and then I'll go up to upper limits -1. Then you gotta fill in the integrand, which we already did, right? Let's try to see if you can use the fraction template here, okay? So if I go alpha F1, we'll see if it works. I'm suspecting maybe it won't, but we'll see. X minus x squared divided by 2 times, I'll go ahead and be tricky and use the cube root button, which is 4. So cube root of x, and then we got to space over to the integral of integration, which is x, and hit enter, and it does it. How about that?
It worked without doing the.
You're wrong.
Unit size, the 1/3.
Yeah, it'll work for that too. Yeah. Okay, pretty cool?
That's a lot.
Wait, why did you
Okay.
do it?
Great.
Well, because it didn't used to. I think the improved operating systems have incorporated that better. Okay, make sense? Okay, so then how could we do stuff like, let's say we want to do something a little different. Let's say that we want to take this same kind of a problem, but now we want to, same function, but different problem. Let's say I want to know, ask something different. Let's say we want to know the average value. What if I gave this to you? Find average value of this. We'll just call it f of x. How about? On the interval from -8 to -1. Well, how do we define the average value of a function again from yesterday? So I'm gonna take it's just the area under the curve divided by what?
B minus A.
B minus a, the width of the interval, right? Because remember, all we're trying to do with this is just grind down the function and make it rectangular instead of curvy, right? And if we grind it down and make it rectangular, then the height of the rectangle is going to be the area, or the average value of the function, right? The area under the curve stays the same, right? So we know the area of the rectangle is the same as the area under the curve, right? And the area of the rectangle divided by its width would give you its height, right? So all I've got to do then is take this answer and just divide by the quantity -1 minus -8, a minus, or b minus a, right?
Mm-hmm.
Which I know is 7. I can just divide by 7. And that's the answer. Okay? So what if I even asked something harder? What if I wanted you to find, so we define the average value of the function as f of c, right? So this would have probably been something like, find the average value, which we call f of c on this interval, okay? Now what if I want to know, find all the values of c? Okay, so this is even tougher. In other words, I want to know the places where the function has its own average value, right? Think of an example like if we were going to drive from Pendleton to Hermiston. Let's say that we just smoothly accelerated up to speed and then we decelerated when we got there. So we can find the average value of my velocity function might be something like 65 miles an hour. Who knows, right? If I want to know, okay, where do I have that value, I'm going to have to go look at the function and say, where is it equal to 65?
Yeah.
And it probably would be at the beginning, and then I'd go faster, and then at the end when I'm slowing down, I need it again, right? That makes sense? So there's two places there where I would have gone my average speed, which was 65 miles an hour, okay? So the same kind of thing here then. How could I find where does the function have this value? All I've got to do now is so I think, unfortunately, I think we have to probably write this down. So f of c is equal to 8.158928571. I wish there's a way you could just grab that value, but I don't think there is.
You can, do you want to practice?
Does it make it a fraction?
Yeah, it's good at math.
Okay.
I don't know if that's
Math, it should.
Yeah, and then it showed the,
Converts
Unless
fraction,
it
but it
can
does,
be a
okay, so it does work out to be an exact fraction.
yeah, it is.
Okay, so f of c is then equal to exactly
4569560.
divided by 560. Okay. And that's probably right. I think that is probably the exact answer, yeah. Okay, so then if we just go back to graph, fortunately we've already got this thing graphed, right? Does anybody know how I can undo that?
You have to like
Just
really
regraph
do
it.
so.
If you regraph it, it works. No, like you put it, like you
Go
have
to
to
the
re-edit
y
it.
equals and
Or if you-
delete the whole sucker.
Or if you just reset the window, that also does it.
There's got to be an easy way to do this. If I go, just turn it on second,
Like it's like clear.
Right.
there's got to be, yeah, and I'd kind of like to know.
I know. It's a smart idea.
Reset your Zoom. Oh, that's true, I could do that. I wonder, real quick, let's just look for something. I think there's a way you can do this easier, though. I think if you go second catalog, and I go down to Alpha Clears, Alpha C. Oh, I didn't do that.
I saw you say.
There we go. So let's see if we can just go down to clear. Did you find something? Other than zooming. 'Cause I don't want, what if I don't want to change my window? There
Clear
should be-
entry?
Might be, let's try clear draw.
Wait, what is that? Clear table.
Let's try clear draw.
Suspension. Oh, yeah.
I sort of don't think that's gonna work, but we'll try it.
Done.
Oh, so it did it.
Wait,
What?
so how did we
I
do
feel
that?
like it'd be faster just to re-enter the same exact scenery.
Mine went directly in,
Maybe.
it didn't go back to
No,
the
you just
window and
gotta
say
turn it
done, it went directly to the graph.
Okay.
Wait, what was that? How do you get the catalog? That seems like a lot.
Well, okay, there must be an easier way to do that
Oh
too.
shoot, I just cleared it. Nope.
There must be a way, like if we go, I just wanna see if I go second format,
If you, no, go second program.
second program.
Yeah, right there, your
Oh.
hand's like right on.
Yeah, so, okay, so, oh,
And just as the person,
that's good. Very good. So second draw and then enter, get clear draw and it'll clear, that's good. Yeah, I'm glad we figured that out. I've never known how to do that.
Wow.
Okay, so now we've got our, right, so we've got our function. All we've gotta do, if we wanna find the places where our function has a certain value, what do? Plug it in where? Can't plug it in for the x because this is a y value, right? This is the average value of the function. Okay? But I could go back to my y equals and go down to y2 and just enter that fraction, right? So then we go 4, 5, 6, 9 divided by 560 graph, and there it is, right? And so now this gives me a visual representation too. If I were adding up the area under the curve, this is the height of the rectangle our calculus grinder would create when we grind down the function, right? And so we just want to know where do the red and the blue intersect. So then we just go second calc intersect, there you go. And then we just want to, okay, it wants to know, this is kind of annoying, it wants to know what's the first curve and what's the second curve. We've only got two of them. So we just go enter, enter, and then it wants a guess. Well, we're pretty close, that's fine.
I just go enter.
And that's fine, enter, enter, enter is gonna work. Unless you have multiple values, and then you gotta kind of have to go close to one of them.
But once you graphed it,
Where's the
Second calc, intersect, enter, enter, and then travel close to an intersection if you need to. If there are multiple intersections, travel close to one of them and then hit enter. Otherwise, just triple enter. And so what's that tell us? It tells us that the x value where this happens, okay, the x value where this happens is at negative 4.636 blah, 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 okay?
And so
Right.
that, but what is that actually? That's where our that's when we're going our fastest speed.
That's when we're going our average speed, right? So that's the value right here. And once again, if we look at these areas under the curves, I just want you to see visually, this will probably be helpful. So if we go back, oh, not there, if we go to graph, okay. If we go second calc, and let's go 7. So we're gonna find the area under the curve from -8 to -1. So there's the blue area, right? That's the area under the curve from -8 to -1, but when we bring in our calculus grinder and we grind this thing down and reshape it, here's what we get. Now we'll go down to, let's see, we gotta go, so I gotta go down to the other curve. Can I do that?
you have to press.
Oh, I think I have to go
If you press trace, I think we can do.
trace up. So I'm on this curve now. I probably could have done it from within the program too. So if I go second calc and I do number 7, now I think I could jump around. See, look, it put me back on the blue curve, but if I go up to the, now I'm on the red curve, right? So now I want the lower limit for the red curve. So I'm gonna do the same thing. I'm gonna go -8, enter, -1, enter, and look what it does.
Is the red the same as the blue?
Exactly. So the red's the same area as the blue, right? See what we're saying? Notice we get the same value back. And so if we want to know when does the blue function have its average value, well, it's where the blue curve crosses the red curve. Right?
Yeah.
Everybody see that? Okay, so that's pretty helpful.
And how did we get the negative, the 45 words or something?
Okay, because that was the
Area over b minus a.
yeah, area over b minus a. So it's the area of the blue function, same as the area of the red function, right? They're equal, divided by the width. And for a rectangle, area equals length times width, right? So the area divided by the length would give you the height, we'll call it. Yeah. Yeah. Mhm.
Could you show the rectangle thing one more time?
Sure. What do you mean by the rectangle thing?
Like how I got how you got the red line intersect, but how it went down.
Oh, yeah. Okay, how I got the intersection of the two?
No, the right after that.
Oh, this part right here?
Yeah.
Okay, you don't ever really need to do that. Because you know that if I were to graph the area of the rectangle, it's going to be the same as the blue function, right? And so really, we already knew the answer because remember, I had to put this number in there to get that line to graph anyway. So I had already taken advantage of the fact that this value, the height of the rectangle, I already did the blue area, which my calculator gave me, 57 point blah 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 1125 or something, right? Divided by the width of the rectangle would have given me the height of the rectangle, and that's all I needed. I didn't really need to actually, I just graphed it so you guys could see what it looked like, but there's no value in that, okay? Practical value, okay? Make sense? Okay, I think, okay, there's one I want to do, and then we'll call it, and we'll use the calculator to get this answer. So let me clear everything. Okay, so now, what if I told you, which one did I assign? I think I assigned respiratory cycle. Okay, so let's do this one from our book.
Do anything.
You betcha. What is it?
Mr. Oya, can I go ask the office if they can excuse me
Yeah.
for the track meet?
Yeah.
from-
Okay.
Thank you.
So close.
Oh, I'm already confused.
Okay, so let's have a look at this. This is a pretty cool question. This is the kind of thing, and this is real world stuff. I mean, this is something that would be valuable to know. So the velocity of the flow of blood at a distance r from the central axis of an artery radius capital R is given to us by, like I picked red there, by that function, okay? So if we look at a cross section of the artery then, really this is all we're doing, right? Here's the artery, and here's a cross section of the artery. And so we've got this central axis that just travels down the middle of the artery, right? And if you think about, this is what's called laminar flow in physics. Laminar, it's a good model for fluid flow. You just think of like concentric shells of fluid, right? So if you got this pipe, the flow of fluid is fastest through the exact center of the pipe. Think of like a pencil lead, well, right down the middle of the pipe. And then if you go out a little bit, and so you're going to create another little cylinder that's going to enclose the pencil lead. Then there's another one that encloses that, and another one that encloses that. So it looks like nested tin cans or something, or cycle, right? That's what it ends up looking like. So the ones closer to the middle, those are the ones that travel the fastest, and every layer outward travels a little bit more slowly, which makes sense if you think about it, right? Because, well, think about flow through a pipe.
And
Where-
it's got more mass on it, wouldn't it?
Well, there's a couple things that happen. So just the physics of this, if you really think about what's going on, this is a great model that makes physical sense. Where's the fluid, obviously, any kind of a fluid, gonna flow the slowest? On the edge, how come? Because there's some friction with the surface, right? Okay, so then that's gonna get slowed down because it's rubbing against the surface. Well, then wouldn't the layer next to that go a little faster, but it's still gonna get slowed down by the fluid next to the edge, right? And so as you move to the middle, each layer of flow is gonna move a little bit faster, but it's gonna be slowed by the slowpoke layer next to it. So the fastest one's gonna be in the exact middle, right?
Yeah.
So that's just the model called laminar flow.
But is the middle one still friction or?
Well, it's gonna have some friction with the fluid around it, right, but it's got the least friction, okay? So if we travel out some distance, by the way, the radius of the whole thing we're gonna say is capital R, right? But if I travel out some distance, little r, and so there's gonna be the layer of flow, right? So this is little r. This is what predicts the velocity of the flow, okay? Does that make sense? So where k is gonna be some constant of proportionality, and it's a real constant. It would depend on the parameters of your blood. Your blood's gonna have a certain, everybody's blood is a little bit different. It's got higher platelet count or lower platelet count. It's got more lipids in the blood, whatever it is. But I mean, either way you look at it, there's gonna be, some people are gonna have more viscous blood than other people are, right? And so that's gonna have an impact on K. It's gonna determine how fast your blood's gonna flow. But for a given person, for a given value of K, we should be able to come up with an equation that's gonna predict, based on the radius of the artery and the value of K, it should predict what the average rate of flow is, okay? And everybody's artery is gonna have a little different radius too, right? Just that's part of your own anatomy. So what are we gonna do? This involves a little calculus, doesn't it?
And
So I'm gonna have to integrate, right? I'm gonna have to find what I wanna do is I wanna find the integral of this function, which predicts velocity, right? From the center to the edge of the artery, and then just divide that by the width of that interval, right? So really what I'm looking at is, you can't confuse the graph that we're gonna draw, the calculus graph we're gonna draw, with the physical situation. In calculus, what we wanna do is take this relationship, and we wanna graph something like this, right? We wanna have velocity or speed as a function of radius, right? Does that make sense? And this is the function, okay? So we know what that function's basically gonna look like. Little r is the only variable in the whole thing, right? Everything else is just gonna be a constant. So we're gonna end up with, this is really just some constant minus r squared, right? Well, doesn't that just look like, if I'm subtracting r squared, doesn't that just look like, yeah, like an upside down parabola, so something like that, right? Does that make sense? Hang on a second. So, yeah. that make sense? So 0 is where it's going to be the fastest, for sure, because that's the center. Little r equals 0 corresponds to the center of the artery, right?
Yeah.
Okay? And then where it's going to be the slowest is going to be, in fact, 0 is going to be at capital R, or right at the very edge of the blood vessel, right?
Yeah.
Okay? So we're just trying to find the area under this curve divided by its width, right? So what's the area under the curve then? Well, so we're going to calculate the integral of k times capital R squared minus little r squared dr from 0 to r, right?
Yeah.
Okay, well, capital R is a constant and little r is a constant, right? And we could take this k from the very beginning and just pull that out front, right? Because that's a constant that's being multiplied by the whole thing, right? So we get k times the integral of capital R squared minus little r squared dr. And now we can just anti-differentiate this term by term, right? So we get k times what? Well, what's going to be the antiderivative of capital R squared?
1, 3.
Okay, but capital R is a constant, right? Just like pi or 7.
For R.
So that's, it's just going to be, so well, let's write it as a separate integral. So it's the integral of capital R squared d little r from 0 to r minus the integral of little r squared dr from 0 to big R, right? Which is, do we have a room? Man, they don't give me enough room on here, do they?
You need a bigger,
Yeah, board that goes all the way around.
I know, that's what I need.
the entire
Ginormous.
wall, the entire wall.
Okay, so this one right here just becomes k. I can pull that big R squared out front because it's a constant. Big R squared times the integral of d little r from 0 to r minus the integral of r squared dr. Well, what's the integral of 1 dr? R. Right, so this one just becomes k times big R squared times little r from 0 to r, right? Minus, what's the antiderivative of little r squared? R cubed over 3. Little r cubed over 3, right? From 0 to big R. Okay? So that's just, and it's k times the whole thing. So there's k times, well, this is just going to be big R squared times, what's that give us? Big R minus 0, right? Minus 1/3 times, pull the 1/3 out, R cubed from big R to 0, which is just going to be big R cubed minus 0 cubed, right? So what is that? K times big R cubed minus
1/3.
big R cubed over 3. Well, isn't that just k times 2/3 big R cubed? There it is. So that's the average speed of the blood flow based on the radius of your arteries and whatever k